Thank you to Mel Science for sponsoring this episode. Mel Science is a subscription service that offers monthly science boxes, which combines hands-on experiments with VR and AR technologies to engage all of us in studying science. They strive to make serious science accessible, interesting, and more importantly, look pretty cool. So the kit that we've got for this episode is almost perfect for it. It is the Alternative Energy Science Kit. And again, this is simply one kit from their physics section. They actually have multiple sections, which includes physics, chemistry, and then a general STEM kit. So again, this is simply one kit from the physics section. And yeah, as you can see, Parker currently is attempting to build himself a solar cell, which then connects into a light. And when the sunlight hits it, it turns on. Voila. And then he also actually creates a windmill, which I find pretty fancy. And when he blows on it, the same light turns on. So again, all these cool things just to learn a little bit more about these processes, especially at your home. Now, within the first month of this episode airing, if you click the promo code link in the description below, you will get a clean 60% discount on your very first month of subscription with Mel Science. And again, now this can include any of the boxes. It can include the physics boxes, the chemistry boxes, or the general STEM boxes. So why don't you get yourself an experiment, try it out with your family and kids, and if you like it, see if you want to continue. So once again, thank you to Mel Science, and enjoy the episode.
It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you back to episode number 106, where today we are going to be talking about the history of physics. Long time coming. Haven't done one of these for give or take 5-6 episodes. So a lot of people have requested these particular individuals, and I think we also love them, especially with all our history of electricity and magnetism. So today we're going to be talking about Michael Faraday and Nikola Tesla.
Yeah, and these two figures in the history of physics were actually recommended by a listener. He gave us a bunch of recommendations, so thank you for that. And, these guys do go very well together because they're both in the electromagnetism world, which, Rehan and I have covered very slightly in university. So we have a little bit to talk about, of course. I'm speaking more on the side of Tesla here. He was a huge inventor at the time, and he has a lot of things that we're not going to be able to cover entirely on the podcast for two reasons. One, there's just a lot of them, and two, some of them I'm just not even qualified to comment on these things because they're so complicated, and he was just an absolute genius. And, he did some crazy things that even though it was 100 and something years ago, people today who are in university studying physics still have trouble grasping.
Not only grasping, but I feel like because these individuals were so, I think we were talking about it the other day, they were so in-depth into their field, they were already so into, so deep into their field, the things that they proved, the things that they did, that for someone just starting out, it would be like, oh, what is that? You know what I mean? They start very heavy to start with, you know what I mean? So it's not like they're just discovering something on the surface. They're, especially with Tesla, he goes very, very deep in those inventions. And to really understand how those inventions work, you need to have a very solid understanding about, the theory or what was already discovered. So on the other hand, while Tesla was mainly an inventor, I'm not going to take it away from Faraday, but he was more of a discoverer. He did more discovery than invention. He discovered, actually, I guess, do you discover a process? I guess you kind of can also invent a process. I mean, that's a whole discussion for a whole episode. But mainly with Faraday as well. He discovered a lot of important phenomenon in electromagnetism. So I believe electromagnetism was still a theory before Faraday. Again, when I say before, I mean before he came out with it. So I think electromagnetism just took off in like the 1820s, and Faraday started doing all his research in the 20s itself. So I believe, correct me if I'm wrong, but I think that was like the era of, discovering that electricity and magnetism are kind of one in the similar. And then it just simply went on and on until Tesla himself used the findings, a lot of findings. I think you're going to talk about that today, Parker. He used the findings of Faraday in his work. And then obviously using all of those cumulative findings, then we have people like James Clerk Maxwell that then formulated the Maxwell equations, even though he didn't technically write it, to then see what we have today, right? So it's all these small pieces of a puzzle that make it up. And that's the whole purpose of history of physics, right? Building that puzzle to where we are today.
Yeah, and I love looking back into the past of physics because right now we are studying what we know today, or I guess kind of the digested version of we're being presented the things that we could understand at our level. And then the more you study, the more you get into the things that we actually know right now. But back in the day, they were figuring these things out that we now just kind of read from a textbook. And so it's even more impressive when you think about these guys that were in the 1800s thinking about invisible waves traveling through the air, space, absolutely just thinking in their heads, this is how it should work, and then doing experiments, proving these things and figuring out properties about these waves and how they're connected to other phenomena like light, how light is connected to electromagnetism, how electricity is connected to magnetism, which today we've said the word many times, electromagnetism, but that wasn't so obvious in the past that these two things were so intertwined. So it's always a blast talking about things from the past. And we've actually done a history of physics episode on James Clerk Maxwell. I forget who the other guy was that we spoke about in that same episode, but that was a cool episode nonetheless.
Wait, we did Maxwell? 1 minute. Did you do Maxwell?
I remember. Yeah, I did.
Okay, because I'm like, what? I don't even remember this episode. We did.
No, I remember, yeah.
There's no way I'm blanking. Okay, sorry. Let's just continue with the quick intros of the podcast. I think you have something for us.
Yeah. We do have a comment of the week, as we always do every single week on this podcast. This week's comment comes from Jet Squire. They say, "Hey, I've listened to this podcast for almost a year now, and it's truly amazing. I study triple science and further maths in my high school, and this has spurred me on even more to do further physics, chem, and further maths, A-level, possibly university, so thank you so much. I've also recently competed in science competitions due to this podcast and really enjoy it. Many thanks."
Wow.
Thank you so much for that comment. I'm so happy when people tell us that we've inspired them to study physics, or not even study physics, but just inspired their curiosity to just kind of think about the world a little bit more. Mm-hmm. That's the entire point of the podcast. So yeah, if you want to be next week's comment of the week, let us know what you think of the podcast. Let us know if the podcast has helped you. And while you're at it, follow this podcast on Spotify and rate it 5 stars. Let's go. Or, follow wherever else you're consuming this.
Okay. Let's dive in. Anything we're forgetting? Nothing. Let's dive in. One thing I wanted to say about just discoveries in general, because I think it's important to realize when people discover things, you have to remember that you have to ask the question, how did they discover it? And most of the times, they discovered it by inventing something that was not invented before. So basically inventing something to discover said phenomenon. So because I know I was talking back and forth with the inventing, discovering really quickly. And I just wanted to point out that because even though Faraday was in fact a discoverer, quote unquote, he is called one of the greatest scientific discoverers of our time, he still is a phenomenal inventor. Like every single thing that he discovered, he had some kind of different way of thinking about an apparatus to set up so that he could discover said phenomenon. So it's not like, he just out of thin air that, oh, this must be how electromagnetism works. No. You invent something pretty cool, see that it works, and then you apply. So I just wanted to point that out. Just a quick little start to the discovery aspect. So maybe we can start with Faraday, because Faraday is earlier, right? When was Tesla born? Faraday was born in
1856.
Oh, 56.
Pretty
so
far,
later.
yeah.
Pretty far. So, yeah, Faraday died in 1867. So, he was hardly 11, 12 years old. Okay. So, Faraday was an Englishman, not the wealthiest family in the world. And interestingly enough, his best part about his upbringing is that he was completely self-taught. Read all his own books, He was very interested in chemistry at a very young age, and he actually got into chemistry. His very first achievements was actually in chemistry. So, who would have thought? And one of the biggest things that he did in chemistry, number one, was literally discovering new compounds, like new organic compounds, by synthesizing. So, synthesis, there are very many ways of either combining or decomposing chemical elements. And one of the big things that he actually discovered, or would this be invented? Maybe discovered, electrolysis. So electrolysis is just a run of electric current through the compound or whatever, and enough electric current will basically, the idea is that it will be able to split the molecules, or not molecules, but the sub-compounds that make it up. So via doing this and via doing a series of this, he actually discovered quite a lot of compounds. He discovered I believe he discovered benzene, which is quite commonly used now, and a bunch of other compounds that I'm not going to be naming at this moment. But a lot of depth into chemistry. And more than that, I think a pretty cool thing that he did was he liquefied gases that at one point were thought to be unliquefiable. Say that again. So most gases exist at a certain temperature. And after a certain temperature, called a critical temperature, no matter how much pressure or whatever you do to the gas, it'll remain a gas because it's too hot. That makes sense. So what he did was he liquefied gases that had a very high critical temperature that were first thought simply to be unliquefiable. They were just like, okay, this is just like a gas. But when this critical temperature is much, much above ambient temperature, you can think that, okay, it's not intuitive to just, apply pressure or whatever you want to liquefy it. So he made this whole apparatus, again, kind of going into the inventions, then discovery. He made this whole apparatus where, what would he do? Okay, he made this apparatus where, I'm totally blanking. Why am I blanking? I'm trying to picture it and I'm trying to explain it in the perfect way. It had an ice bath, right? It had an ice bath. It obviously had a barometer to measure pressure. And I'm forgetting the exact about how he increased the pressure, but the idea, I can give you the theory. The idea was that, remember, because these gases have such high critical temperature, just pressurizing it won't really do much because, again, the temperature is much higher than ambient. So you have to do something to it to cool it down. So he had, again, if you just simply search up Faraday's ice bath experiment or the Faraday experiment when Faraday's liquefying gases experiment, you'll basically see what I'm trying to picture in my head. But I can't really picture the pump, so I can't really explain it very well. But the idea, again, not an actual pump, of course, but the idea is that he pressured the gas while cooling it down. So he removes sufficient energy from the gas to bring its critical temperature lower. And then with sufficient pressure, he was then able to liquefy it. So that was a big thing that he did, the liquefaction of high critical temperature gases. Now, obviously, we have much more sophisticated methods, but he was one of the first individuals to do so with a gas that has critical temperature above ambient. Because again, if it's ambient temperature, then then you just, pressurize a gas, voila, you got a liquid. But again, what if the critical temperature, I'm forgetting the one that I read this morning again. I think it's carbon dioxide. It could be. No, that's like 40 degrees. No, that can't be it. Some compounds have like 50, 60 degree critical temperature, 70 degree critical temperature. So if you just have the gas with the atmosphere and you just start pressurizing it, that's not really going to do much, right? So you have to figure out a way to cool it down efficiently. So that was one big thing that Faraday, brought into the line of chemistry. I wanted to bring out the chemistry thing first because we're both more interested in the physics part of it. So I just wanted to let everyone know that he was still a chemist. But yeah.
So this is a direct application of the ideal gas law, which was not so obvious at the time of this experiment that he was conducting. But I wanted to ask, if the critical temperature is higher than, let's say, ambient temperature, wouldn't you want to decrease the pressure? Because, wait, what I'm thinking of is if the critical
PV
temperature is
equals
higher...
I know what you're thinking of right now. I know what you're thinking
No, because...
Yeah.
But listen, if the critical temperature is higher, isn't that the temperature to evaporate, right?
Yeah, so the higher the temperature, the more technically
but if
energy
you
the more
already
gaseous it is.
If you already have the gas, right?
Yeah.
And that means the pressure is lower because it's an ambient temperature or something like that, right?
Right, but remember the critical temperature means after this temperature, no matter what you do to the gas, nothing will happen. So when that temperature is low, such as the compounds that we had already liquefied, we had obviously already liquefied gases. He didn't invent liquefying gases, right? So we had already liquefied gases. So when that temperature is low, we can liquefy it much easier. But when that temperature is much higher than ambient, we need to figure out a way to effectively cool it down while still pressurizing it. Because remember, PV equals nRT. So when you apply pressure, if you're keeping the volume the same, your temperature is increasing. That's not what you want. So you want to figure out a way.
But also, how do you even increase the pressure without changing the volume or the number of particles? Because
there was definitely a volume change. There was definitely obviously a volume change that happened in this. I mean,
but I guess,
but there was most.
But the goal is to keep, the goal is to have the pressure increase more than the volume decreases in like proportional terms, because you want the whole thing to go up.
Right. So let's read a quick statement. Faraday was able to liquefy gases with high critical temperatures such as chlorine, hydrogen bromide, and carbon dioxide. Oh, so I was right. Oh, carbon dioxide is one of them. By the application of pressure alone. Okay, then they don't actually go into... Okay, so they don't actually go deep into how they did it. What a useless website. Never mind.
Nice.
I was all excited to start explaining how it happens. Because I think the reason why a lot of these things are also lost because in the moment, like while they were actually conducting these experiments, like a lot of these were like just... What's the term that I'm looking for? Brute force. They're just brute force methods. You know, they were just like, oh, we're just gonna force it in a way. So not every single thing that they did might have been, again, I'm just guessing because, again, I've looked at my sufficient share of websites and have not been able to find like a very concrete explanation of the liquefaction. Obviously, it might exist in like a paper or something, but I didn't go that deep. So I'm just assuming that not every single step might have been like exactly written down, because one day it might have been like, oh, it didn't work, let's just try this instead. Oh, that didn't work, let's just make this cooler. You know what I mean? So there might have been like, again, it is actually called this was called a brute force method that he actually used to do said pressurization. So it wasn't like very concrete, but the fact that he did it was big. That's it. That was the main thing. It was just like, hey, that's cool, you did it. So,
all right. I guess I can talk about Tesla a little bit.
Shoot.
Introducing Nikola Tesla. So as I mentioned before, he was born in the year 1856. So a little bit, after the era of Faraday. He was born and raised in the Austrian Empire. Technically, he's a Serbian American inventor. He actually comes from a line of inventors on his mother's side. And his mother was actually very fond of training her memory. She famously had a really good memory, and she trained Nikola at a very young age to also have a really good memory. When he was a kid, he learned up to 8 languages. This was just his thing. And actually, I think this somehow contributed to his success as an inventor. He claims that he would get ideas for inventions in flashes of light in his vision. He would get these flashes of light, and these like machines or inventions or ideas would just build themselves up in their head. They would modify, they would kind of change until they were just right. And then he would even test them in his head, and then he would go build them, right? And there's even a quote. He said, invariably, my ideas work as I conceived that it should. And the experiment comes out exactly as I planned it. And in 20 years, there has not been a single exception. So he was a mental inventor, I guess you can say. He thought of everything in his head, tested them, and planned it out all in his head before even starting the actual physical experiment or invention. And, as he said, it worked every single time. And, call me a speculator here, but I think that his mother's influence on him as a child in training his memory kind of led into that ability to use his mind to construct these objects. Because when you're training your mind and you're training your memory, one very famous technique for remembering is tying memories to objects or tying memories to places that you know very well. And this kind of association builds up your mental, I don't want to say imagination, but like this mental kind of gymnastics that you can perform in your head. It gets clearer, more effective, ... So that's kind of a light introduction into the mind of Nikola Tesla. He studied physics and electrical engineering, I think mechanical engineering as well in school, but he never actually got his degree. He just dropped out. But he did gain a lot of experience by just going and working for companies. He worked in the electric power industry, and he also did work in telephony, which was a huge thing back in the day because phones were, like actual landline phones were just coming out. They were hot on the press. It's like the new iPhone 13. He was kind of like the Apple engineer of the phone of the 1800s, right? Which, fair enough. Today, if you want to work in IT, or the big thing that's out right now, you go and you work for the big companies, right? Apple, Amazon, these huge companies. Back in the day where people were just starting to build massive infrastructure in terms of electricity and mechanical things. Cars weren't even out. It was still kind of like a chariot type deal. Nikola Tesla actually invented motors. That's the place and time that we're at, where motors were coming out. So he was placing himself in that industry where he would push technology to its limits at the time. So yeah.
Wow. Yeah, Nikola Tesla, if I'm not mistaken, I think you told me this quote, right? You say the Einstein quote. I think that's a very good introduction to Nikola Tesla.
Actually, hold on. I did a little bit more research, and I don't think...
Oh, no.
I don't think it's a quote.
That was such
It's just
cool
a saying.
quote. Okay.
Well, here's the thing. We don't actually know for sure if it's a quote, but based on their ideologies, Tesla disagreed with a lot of Einstein's work, and Einstein was known to be very confrontational with people who disagreed with his ideas. Let's think about, the Niels Bohr versus Einstein kind of debacle. But based on that kind of evidence, it's highly improbable that he would have said this, but there is a saying going around that goes like, Einstein was asked, how does it feel to be the smartest person alive? And he said, I don't know, ask Tesla.
Bam.
And the thing is, Tesla is, first of all, was a straight up genius. Let's just get that out of the way.
Yeah, for sure.
But secondly, he wasn't even given, I don't think, personally, he wasn't given the credit that he deserved. Like, why is it that when I'm
Edison.
in, why is it that in high school and even I don't know if I learned this in elementary school, but I remember in like grade 6, we were playing around with light bulbs and circuits and stuff. And I'm sure the name Edison came up. And, more so in high school, you think about Edison, but the power that we use in our homes right now, my home and in your home, is AC. The person who was very against AC was Thomas Edison. he was pushing direct current for monetary purposes. He owned a lot of patents, and I'm going to talk about this a little bit later. But very interesting, shady stuff going around. The fact that we don't talk about Tesla in school when learning about electricity is it's beyond me.
Yeah, I guess usually we just because Edison is always like put to, oh, he invented the light bulb. First of all, I hope for you guys listening out there, you know that he didn't. He simply has the patent for that invention. He did not invent the light bulb. It's a whole bad, evil story that comes along with Edison that if you have a really good, view about him, don't read that because that might destroy it really hard. So
no, read that. Get the facts.
or do that. Yeah. So I guess there's a lot of that also. A lot of politics. Unfortunately, science has a lot of politics. Like even though we don't want that, like not politics, but I mean like between each other. Like even Newton time. Even in 1600s, that guy was a bully.
Mm-hmm.
So it's been the same throughout. It probably will be the same throughout. But
Newton was actually hiding proofs from the world.
Like who would do that?
Yeah.
Like
he was hiding them.
that. Anyways.
Yeah.
So you were mentioning that Tesla invented the motor. I'm not sure if that's true. Maybe he invented
No, he didn't. No. He didn't invent the motor. But he was in that realm. Like he worked on I think it's called a dynamo generator, motor, something like that.
AC. Right.
Yeah, which is basically injecting his take on that kind of industry, right? Because he was the whole AC guy, and then he wanted to, think of something to what am I trying to say here? In the motor world.
All of these things, actually, the dynamo, for example, that all comes from Faraday's understanding of electromagnetism. So this is why this history of physics episode is beautiful, because it all comes together. Like the dynamo is literally based on rotating magnetic fields, which then induces an electric current, and voila, we have electricity. So it's all based on just using Faraday. So the reason I said I don't think Tesla invented the motor is because Faraday did. So Faraday actually invented like the first very, very basic form of converting electrical energy into motion. So what he did, backtrack. So 1820, right? 1820 was the first, not proof, but I think it was the first theory. It was by Hans Ørsted. Very famous name, actually, Ørsted. I think we've definitely heard the name before. But he was the first individual that proposed that electricity and magnetism were one and the same thing. The reason that I don't know if he discovered or he saw this or someone else saw this and he's inferred it, but when an electric current ran through a wire, a magnetic needle would deflect. So that means there's some magnetic influence in this purely electrical circuit. And then I believe it was, who was it? Oh, no, sorry, it was Ampere. It was Ampere who discovered this magnetic needle deflection. So I think Ørsted maybe just had a theory of how they existed because, again, remember, electricity and magnetism were two separate things at this time. There was no electromagnetism. So Faraday comes in the picture and starts messing around with these experiments, starts messing around with Ørsted's experiments, starts seeing, okay, what type of magnetic field is created around these wires. And what we know today is that this type is circular. It's a circular magnetic field. So he thought, if I can isolate a pole, which now we know doesn't exist yet, a monopole, then I should be able to attract this this magnetic field that's working in the circuit to this pole, to some monopole, quote unquote. So what he did, started, testing up like most physicists do, and he had a bath of mercury. In it, he put a permanent magnet. In this, now on this magnet, I believe there was a wire, wasn't touching it, was a circular wire. Obviously, the orientation is very important. Remember, these fields go in specific directions. So
right hand rule.
I don't think that was a thing back then, right? I mean,
it wasn't called the right hand rule, but I'm sure.
Okay.
No, but they knew about cross products and
they knew about
how it.
Yeah. They knew about how exactly, or not how exactly, but like they knew roughly about how it worked. But at this time, magnetic fields were thought of as something that was flowing, as something like for example, think about the wires as think about the electricity in the wires as water moving through the wires. That's how it was originally thought of, how electricity was thought of. That is flowing through the wires. But then Faraday saw it a little differently. He saw electricity as minute vibrations in these wires that then propagate to somewhere. Well, now we know the whole electric field theory and everything, and now we know it's kind of one and the same thing, but that's what they thought at that time, right? So what he did was he basically hooked up these wires back to the apparatus, back to that experiment. He hooked up these wires to a battery. When he ran a current through this circuit that's on top of the wire, he found that this circuit would start to rotate. And he called it the first, was it called a rotator engine? Or like the electric, it was basically the first engine, or the first, not engine, but the first motor that converted electrical energy into circular motion. So this,
and you can actually do this, right?
Moving. Of course, you can do
if
it.
If you just get a battery and then you just put some copper wires that go around it and it'll start rotating.
It will be a little harder because you would need to isolate one of them, unless you can because you need to put because you would need to put the what do you call it? You need to put the magnet in a bath of something that doesn't conduct electricity, or that wouldn't affect the magnetic field. So what he did, again, as I mentioned, he put it in a bath of mercury. But I'm sure, I don't know, do other things exist that we can, I'm assuming, put in to isolate one of the
I'm just saying the same idea kind of
the
you
idea
can do at home.
Right. The idea is always there, right? So one of the things that he got from this whole thing was that, hey, I've kind of seen how we can now convert this electrical energy into motion. And with that thought, he actually invented quite a few things to do said same thing. He, again, I don't want to actually get into it, but he also invented this disc experiment where when he ran a circuit through it, the disc would rotate. So he had a lot of cool ideas where he implemented this idea of electric fields and magnetic fields are related. So how do we use them together, right? That was his idea. Then comes a big discovery in terms of Faraday, and that is electromagnetic induction, or at least like let's just start with like the simple induction. So one of the big, I believe he had quite a few experiments showing induction, right? I'm just gonna talk about the one that I think I number one understand the best, and also it plays really well into Faraday's cage. So,
but they're all pretty similar in nature, right?
Yes.
I think what you're referring to, it's in that one page in Griffiths, right, where he puts all three beside each other.
Yes.
Is it? Okay.
I mean, that's basically the idea that I'm trying to get into. But again, the experiment is a little different. But yeah, the idea is the same. So, as I mentioned, as you very well said, most of his things, the three laws, I know what you're talking about. They're basically identical. They're basically one law. But it is just Faraday's law of induction. That I'm going to get to in a second. But how he actually discovered it, I don't know if it's like the exact one. I don't know if I don't even know if people know which exact one he used. But he had a multiple set of experiments. All of them did similar things. So what did they do? This one I'm going to talk about is called the ice pail experiment. Really cool. He puts an ice pail, so it's like just like a bucket, right? Connected to like there are wires at the bottom of that bucket, connected to a like something that can read electrical current. There's no way I'm forgetting this right now. What was it called back then? It was obviously far enough from the apparatus so that it wouldn't be disturbed. Oh shoot, I'm forgetting.
Wait, something that can read current, like a multimeter.
No. Well, that's today. That's very sophisticated. No, they didn't have multimeters back then, right? The ice pail experiment. Wait, I'm gonna just look it up right now. So the ice pail experiment had sensitive detector. Oh, gold. Electroscope. So an electroscope, and this was called a gold leaf electroscope. This was like back in the days, and now we have modern electroscopes, but multimeters like basically are just that times 100. But so it basically simply measures electrical charge, right? Very, very sensitive to electrical charge. And what he did was pretty cool. So remember, this bucket is like, it's a metal bucket, right? So it's the conductor of electricity. Not charged, nothing. There's no reading right now, right? No reading. What he does is he takes a metal ball, charges it up with static. So this has a net charge right now. And he puts it in the bucket without touching the wires. Recall, without touching the wires. And I think you can kind of see where the story is going here. What he saw was that the bucket, the wires, remember, are connected to the outside of the bucket. That's connected to the electroscope. The bucket now exhibited a net charge. And he's like, that's interesting. I just moved this static or this electrical ball towards or inside of this bucket, and all of a sudden, the outside of the bucket has some kind of charge. What is that? And that was basically one of the first. Again, I'm not sure. Don't quote me of saying the first, but it was one of the experiments that led him to discover electric induction, or just like, I mean, the whole electromagnetic thing is kind of synonymous.
But that's not an example of induced current, though. That's just induced charge. Yeah.
Well, again, that's what I'm just saying. I'm just saying induction. This is just showing that, hey, you can induce a charge on this bucket. Now, the best thing about this was that as he was moving this charge inside of this bucket, this is actually more of a conductor / Faraday cage experiment. So as he was moving this what do you call it? This ball, right? The sphere inside of this bucket, he saw that there's no change in reading to the electrical signal. So what that was telling him was that no matter what happens on the inside, and this is a big one, no matter what happens on the inside of this metal, the charges on the outside distribute themselves such that no matter what happens in the inside, nothing happens, like nothing changes. So basically what he invented was the modern, or not modern, but was the Faraday cage, right? So a quick lesson on a Faraday cage. A Faraday cage is basically a conductor, right? Any kind of conductor. Does it even have to be? Yeah, obviously, because it has to.
It does, yeah.
Right, obviously. So a conductor with a charge, or not, it doesn't even have to be a charge. The idea is that it's a conductor. It's a hollow conductor. So it has like a surface. Now, the idea of a Faraday cage is whatever happens on the inside will not affect the outside, and vice versa. So if an electrical charge were to, or electrical field were to be sent along the sides of the conductor, in this case, the conductor, remember, is the ice pail, the bucket, right? If an electrical field were to be sent alongside this bucket, the charges on the outside, remember, protons and electrons still exist. Like, just because it's not charged doesn't mean they don't have, doesn't mean that's not there. So again, when I say positively charged, it's not protons, it's just lack of electrons. So the idea is that when an electric field is sent through this pail, bucket, or whatever conductor, the charges on the outside of the surface arrange themselves such that the fields inside cancel each other out. And this is the beauty of conductors, which will always work. And this is one of Faraday's law, not Faraday's laws, but one of his discoveries, that no matter what you do inside of the conductor, right, if you place a charge, the net charge hasn't changed, right, because there's a positive and a negative on each side of the wall. However, what you will notice is that the outside is now charged, right? So whatever you do on the inside, the outside will remain charged. You take it out, it's still going to remain charged, but the net charge of the whole ice pail bucket does not change, right? So that's
actually an application of Gauss's law.
Well, Gauss was after, right?
Yeah, no, but this is an application. It can be explained using Gauss's law, because if you put a charge inside of a hollow sphere, then if you draw your Gaussian surface around that charge, then you get, let's say charge Q. But then, because you can make some conclusions about conductors just using like physical arguments, and one of those conclusions is that the net charge inside of a conductor is zero. Otherwise, you would get charges moving around and forces being applied on those charges where that would make no sense. So then if you increase your Gaussian surface to be inside the conductor, the net charge has to be zero, which means that on the inside surface, there has to be a charge of minus Q to cancel out. And then if a charge of minus Q gathers on the inside surface, then because the conductor was neutral, then a net charge of Q has to be on the outside surface.
Exactly. And this basically kind of proves us why, or not proves, but tells us why you want to be inside a car during a lightning strike, because the car acts as a conductor. So the outside of the surface of the car basically just rides the electricity, while the inside is perfectly secure because it's basically a giant metal box that you're sitting inside, which is exactly what a conductor is. Mm-hmm. Interestingly enough, so the law, Gauss's law, was first formulated by Lagrange in 1773. But then Gauss, I'm assuming, just perfected it, or like did it more on the attraction of ellipsoids in 1835. So all of this was at the, like very same times. Very, very similar. Like 1835. This was definitely before, though. Like this experiment, like I feel like the ice pail experiment, when was it? 1843. Oh, this was after. Oh, no way. So I guess you can use Gauss's interpretation for this stuff. Yeah, I guess that works, yeah.
Well, fantastic. Do you know if, well, it definitely is related to like electromagnetic shielding.
Right.
I think this is done with a Faraday cage, right?
Yeah.
Because if you're inside of a Faraday cage, information about the electromagnetic fields inside cannot be communicated to the outside. And I read about this yesterday. And I don't know if this is because or an effect of the Faraday thing that you were talking about. Right. But if you have a cavity inside of a conductor or multiple cavities and you randomly distribute a total charge of, let's say, capital Q, right? But that total charge can be subdivided into different charges that are put into these different cavities.
Right.
There is no way of knowing how those charges are distributed within the conductor just by looking at the outside of the conductor.
Yeah.
And I think this is called like electromagnetic shielding, I'm pretty sure. And I think I remember in first year in my lecture, the Professor Julian put an image of one of these cages, and he's like, this was like, in the past, this was used for like anti-spy situations.
Oh, wow.
Where like they would put people inside of these cages just so they could be 100% sure that like nobody was spying on them. Or, yeah.
Well, I mean, that Faraday cages also completely block out any other type of radiation as well, which is why you have, or not radiation, but like electromagnetic things, which is also why you have like antennas or like some kind of receivers on the car, because it won't go like through the car itself. I mean, you have glass and everything on the car, which obviously changes the conductor state of it. But what I'm trying to say is that the theory still applies. But yes, it is in fact electromagnetic shielding. But that is a pretty messed up thing that people used to do.
Well, no, I don't know if I'm just dreaming right now, but I think I remember this being a topic of conversation.
So actually, I think Faraday. I just want to finish up with Faraday cages because he himself is a famous thing. In 1836, he himself stepped in his own cage, like a wooden frame with like mesh wires and everything around it, and then he electrified it, and he basically was like, "Yo, I'm good." And the idea was, one of the big things that this also kind of showed was that electricity in this case was more of a force and less of like a fluid that many people believe. Remember I was saying how Ørsted believed that it was flowing like water? This is also one of the experiments where it was kind of like, well, that's not really true, because that wouldn't happen if these charges were induced in this way. So a lot of discoveries from the induction to the Faraday cage. Obviously, we have Faraday's law of induction as well. That does have to do more to do with magnetic fields as well. But he also did a similar experiment with magnetic induction. I believe he just removed a magnet. It's all there. It's all there. Just different discoveries. These guys have a lot of discoveries, as Parker said in the very beginning of the episode. We will not be getting through all of them. But again, just getting through the theory and most of like the big stuff that they did and how it's important, right? So finally, I think I just want to pull up the law of induction itself, which is kind of a cumulative understanding of a lot of these separate discoveries, right? He was also, and we definitely discussed this on the magnetism episode that we had a couple episodes back, but Faraday's three laws, or basically Faraday's law, was he was just playing around with circuits and a magnet, and he just said, hey, wait, well, what if I move this magnet back and forth? What'll happen? So you got, obviously more complicated than that, but like that was the essence of what he did. And he found out that, hey, a change in magnetic flux. I think we've explained all that before, right? Magnetic flux, maybe we can go over a quick thing again. But a change in magnetic flux induces a current in a wire. And that right there is the theory of dynamos, which is what Tesla used. So a lot of these things come together, I believe, again, we have gone very deep into Faraday's law of induction. So I'm not going to spend another 15 minutes on that. You can go check out the magnetism episode if you want to check it out. But, that was most of his induction stuff. He does have another thing that I'm going to get into after a quick Tesla fact. But, that's most of his induction stuff.
Yeah. Well, I don't know how quick it's going to be because
I said
you've been talking for a while.
My bad. I said quick as in like quick Tesla fact as in a Tesla a Tesla turn.
Yeah. So Tesla was mostly known for his fundamental contributions to the world of alternating currents. And AC, for people who don't know, along with DC, right? These are both different forms in which electric power can be delivered.
Bless you.
Excuse me. So yeah, these are both different forms in which electric power can be delivered. Direct current, you can think of the power output versus time graph as just a line, or I don't think, not power, but voltage.
Right.
As just a
right.
straight line. And then the alternating current is actually one that goes back and forth. It's where the voltage switches, right? And there are different patterns that you can take. Usually it's sinusoidal, but
Right.
You can actually use like square waves or triangular waves. And
I'm sure
this
that's just harder
has
to produce, right? That's just harder to produce, I'm assuming.
I don't know. I mean, probably
Like,
because
yeah,
all
of
of
course.
these
Why
waves
else would they
are
use-
because of
Yeah.
like Fourier. It's
Right,
like a
right.
superposition, so it is probably more complicated. But you can actually use these like AC current in different forms, like square waves or triangular waves in music, where when you use a synthesizer, you can pick like the shape of the wave and it changes the noise. That's because in like a musical output is like a frequency, you know what I mean?
Right.
Which is essentially what AC current is. It's a frequency of voltage that goes up and down.
Right.
And the shape of the wave changes the sound of the
So,
wave, I guess you can say.
I would want to ask, if you don't mind, I would like, to what extent did he invent it? Did he like totally just invent this current, or like what?
Well, you don't really invent these kinds of things. You just use them because they're tools at the end of the day that you can use to do other things, right? It's, as I said, it's a form in which electrical power is delivered. And the way you use that form can be done for many other things. For example, he built an AC radio transmitter to, like, he made the first remote control, or like RC radio remote control device ever. He presented it actually in New York at the Madison Square Garden. It was a boat, a remote control boat.
Oh, damn.
And guess what happened? People said he was doing magic and wizardry. They just didn't believe him. Because, and they just didn't believe him because, imagine if I went into the town center and just started levitating, and I said, it's science. People would say, what is going on right now? It's the exact same thing back in the day. You start moving things with no wires, completely separated. People were going nuts. They were saying, this was a quote from Wikipedia. Some people said that there was a little monkey inside the boat that was trained to move it around, which was not true. There was just a receiver in there. There was just a receiver and a couple wires hooked up to the motor. So, yeah. But just imagine you're living in a wired world, and you're the first guy to pull up and just start controlling things without wires. Inevitably, people will doubt you because this seems like science fiction. But eventually people will realize, damn, this guy is an absolute genius. Other than that, just really quickly, Tesla is known for, well, a lot of things in science are gray area in terms of who did it first. But people think that Tesla is one of the first people to take X-ray photographs. So Tesla, as we've been talking about, was doing a lot of experiments with electromagnetism and electromagnetic waves traveling all over his laboratory. Inevitably caused, there was some film in his laboratory, and after a few experiments, that film was actually damaged, and he was thinking, oh wait, this is like the invisible energetic waves that were traveling through my lab that caused the film to be quote unquote damaged. But actually it was actually these electromagnetic waves causing the film to get imprinted with, well, at the time of that, there was nothing in the way. But as he would soon discover, if you put things in the way like bones or metal, the X-rays would actually get absorbed by certain materials and would pass through other materials like muscle. And then if you were to shine some X-rays on your hand with film on the back of it, the X-rays that would get absorbed, obviously they wouldn't reach the film, and the X-rays that would go right through your hand, they would imprint the film with an X-ray image. And there's a famous picture of his boot. I don't know if you're familiar, Rehan, but it's if you search up first X-ray image, it'll definitely show up. It's actually Nikola Tesla's foot, and he's wearing a boot, and you can see there's nails in his boot, but that's just because that's how they made boots back in the day. They would nail the sole to the bottom of the shoe. And I think they still make shoes like that, but you know, it's a weird sight to see, because there's just like there's his foot bones, and then you see the outline of his shoe, and then nails just sticking through it. It's pretty cool. But yeah, that is very cool.
So he probably gave like a bunch of people cancer, right?
Yes. No, they figured out that it was bad for your health. I don't know if it was that quick, but they figured it out eventually. Yeah. They did find out that it was he actually has a quote here. It said Tesla said he could feel a sharp stinging pain when it entered his body, and again at the place where it passed out. So, and this is when he was doing experiments, because obviously when he figured out that X-ray imaging was a thing, he thought of some experiments, made he used a cathode tube. I'm not going to go into that right now, but he used one of those things to basically shoot X-rays, and yeah.
Do you want to know something cool? You remember how I said Faraday kind of discovered or invented electrolysis? He actually also invented the words for cathode anode.
That's pretty cool.
And a lot of the terms that we use today for like positive and negative charges, he invented.
Oh.
Which is pretty cool. I just love how a lot of these things kind of like just join together.
Yeah.
And Tesla also has some dynamo experience, right? Like, did he invent the dynamo? Did he like kind of? What is a dynamo, right? Like, let's just get into it first while you.
I mean, I don't.
So a dynamo.
Yeah, go ahead.
Or an alternator, right? An alternator is similar. Is basically a wire that is spun rapidly in a magnetic field. So dynamos or alternators are used in almost every application of electrical generation or of like current generation. In cars, for example, when you're braking or when you're gassing, some of that goes to rotating this wire, which then produces electrical current, which can then help if you have an EV, of course, or half if this is hybrid engines only, or a full EV also obviously works in the exact same way, right? By rotating this wire, you are producing electrical current, which is then rotating the wheels. And on braking and whatnot, you take energy from the wheels and charge it up again. So that's just one example. Of course, you have things like, I don't know, you can think of literally anything. Wind turbines. They rotate. They're basically literally rotating this loop of wire that's, again, going in this magnetic field. And what's Faraday's law of induction? As a change in magnetic flux, a change in magnetic flux induces a current along this wire. So as it's rotating along this magnetic field, this value is changing, right? The direction is constantly changing. So it therefore induces a current in specific direction of the alternator. So alternator, dynamo, similar names. But yeah, what did you find? Did he invent it? Did he kind of invent it?
He did. Well, no, he didn't invent the dynamo. But I'm actually thinking, earlier I said that dynamos were related to engines, and I don't think that's right at all. I didn't have.
I mean, what do you mean engines? As in what?
As in like motors
engines?
and stuff. Yeah. It's just
When you
it's a
say
generator.
motor,
It's essentially.
well, yeah. When you say motor, it's a
Okay.
motor.
Well, yeah.
Like it's because like it's rotating. Yeah, it's definitely a motor because it's converting rotational energy into electrical energy. So that's a motor. That it is. Like a motor is just anything that like converts one thing to another.
Well,
You know? So it's definitely a motor.
he
in that
did
case,
design.
but it wouldn't be an engine.
Tesla actually, I guess you could say invented. He invented a dynamo using AC current as the current that passed through the wires. And he actually, I believe he presented this invention to some sort of electrical engineering collective presentation type deal. And somebody there, I think his name is, let me just double check. Westinghouse.
We've heard that. I feel like we've heard that name before.
Westinghouse was his last name. He was there and he bought the patent for that device and actually hired Tesla as a consultant to come work at his company. Because Tesla had actually, in this time period, he left Edison's company. He worked for Edison, but had a big disagreement with him because he was advocating for AC. Edison was saying, no, I want everything to be DC because I own all the patents to DC, which means that I can control all of the money and all of that stuff. And if I start making AC, I'm going to lose a lot of money, so no. And then Nikola Tesla was like, peace, I'm out of here. And so he was out of a job, and this is when Westinghouse picked him up. So,
can you please talk about the Tesla towers?
Yes, I was gonna get.
I feel like that's
get to that.
important. I feel like that's essential.
Yeah. So I think this was Tesla's overarching dream kind of device to create for the world. So the Tesla Tower was actually a means of wireless communication, like a worldwide wireless communication tower. This tower was thought of and designed, and I guess he didn't build it himself because it was huge, but he got investors to buy him some land. He got like a whole like building and a tower built. It looks absolutely insane. It looks like some alien stuff, especially for like the 1800s. Or no, sorry, this was very early 1900s, 1901, 1902. The tower was built in Long Island, and it's called the Wardencliff Tower. So what is happening with the Wardencliff Tower? So Tesla actually has an interview in which he described what the tower does, and so I'll just use that as the explanation, because who better to explain it than Tesla himself? He said, using the Earth itself as the medium for conducting the currents. He's talking about the tower is using the Earth, thus dispensing with wires and all other artificial conductors. A machine which, to explain its operation in plain language, resembled a pump in its action, drawing electricity from the Earth and driving it back into the same at an enormous rate, thus creating ripples or disturbances, which, spreading through the Earth as though a wire, could be detected at great distances by carefully attuned receiving circuits. The quote continues, but imagine this. In a world of wires, this man comes up with the idea to create this huge tower, which is essentially a pump, using his it's so convoluted because this tower uses obviously AC current, right? Going back and forth, pumping and driving and pulling these currents from the actual Earth itself. He was like, you know what? The earth is my wire, and I'm gonna drive these currents into the earth where you could pick up that signal anywhere because the earth is conducting it. And
Right.
what an outlandish idea. But in theory, it would have worked. Unfortunately, other inventors in the world at the time were coming up with other ideas for wireless communication. I forget the dude's name, but he was making a telegraph, which was, I'm pretty sure this was what they used for Morse code. They use a telegraph.
Yeah. Yeah.
And that was...
That's how they invented Morse code, actually, through a telegraph.
So that was a lot cheaper, obviously, than building a gigantic tower to use the earth as a conductor for sending signals. Building a telegraph was a lot cheaper, and things were moving along quicker in that world. And so investors kind of clued in. They're like, you know what? This idea is just too crazy. They pulled out their funding, leaving Tesla with no money, and he was never able to actually finish the Tesla Tower. And we will never know whether this means of worldwide wireless communication could have actually happened using this system. And yeah, somebody, the property went foreclosure. Somebody bought it, tore down the tower, and just made like rental properties on there. It's pretty insane. But now it's actually a museum. The property, it's a museum where they have just stuff about Tesla. And actually, cool.
Yeah,
What's cool is that back in the day, where Tesla was going around when he was out of a job, he was looking for investors to give him money. He would make a laboratory and just build things, and then patent his ideas, and that's how he would get. That's how his investors would get returns on their investments. Just this mad inventor would create a bunch of cool stuff and then patent them, and then obviously when you patent something, you have control over the reproduction and distribution of that thing. So at the time, rich people would actually flex that they would go and visit his laboratories. They'd be like, oh, look at me with Nikola Tesla and this futuristic stuff. Like I'm going to use this analogy again. Imagine if today some like crazy mad scientist had a laboratory where you could just start like levitating, or you could start doing like these crazy things. People would go there and be like, oh, look at me, like I'm doing all these crazy, like out of this world stuff that people couldn't even believe. I would go there. Sounds like a hoot. So yeah.
I think one thing we can end on, so like again, Faraday did have other inventions. Wait, do you have anything more to say on Tesla?
I mean, there's a lot to say, but
yeah, no, that's what I'm saying. But there are still like things to say. Like just like I'm just gonna like really quick brush through them. Like Faraday, for example, also discovered diamagnetism, which is also actually important in a lot of these theories. So we know paramagnetism. It's basically when the electrons in a molecule don't fill up all the shells, so it has a monopole, or not monopole, a
dipole.
No, like dipole, a moment. Sorry, moment. Yeah, not monopole, a moment. So with enough of these atoms arranged in a certain way, a paramagnet basically is partially attractive to a magnet, and a diamagnet is the opposite. It's when all the electrons are full, so it's basically fully charged to the point where it wants to repel from a magnet because it's all in the opposite direction. So he kind of he kind of discovered that as well. He did some few things here and there. There are actually a lot of things that he did.
and I'm sure Tesla did as well. But just one thing I want to end the podcast with, unless you have something else you want to talk about, is the Tesla coil. Just brief, but the Tesla coil. You have anything you want to talk about first?
No, I wanted to talk about Tesla coil.
Okay.
Yeah, well, the reason why I didn't bring this up earlier is because, even though it's one of Tesla's most famous inventions, it is actually very complicated in its nature. You might have seen a Tesla coil. There's a very famous picture of Tesla sitting in a chair. I think he's reading a newspaper or something. And then beside him, there's a gigantic Tesla coil, and there's these discharges. They look very menacing, very dangerous. Kind of looks like lightning. They're called discharges, though. And it's a picture. And it looks like he's about to get electrocuted, but he's just sitting there reading a newspaper. It's actually pretty funny. But a Tesla coil is, well, it's a coil. We'll just say that simply.
It's a coil of wires, right? I mean, this works under the same principle of electromagnetic induction. It's the same thing. It's just that this voltage is like times 10,000.
Yeah, it's very. And one very important thing is that usually people would use direct current back in the day. And he, obviously, as we just spoke about this whole time, was a huge AC guy. And actually, one of the advantages with AC is that you can use very high voltage without losing power through resistance, right? Like through heat.
Attenuation, right.
And so he could make a Tesla coil using alternating current, and it would be much more efficient than using direct current. So a Tesla coil is made up of complicated stuff.
Simple.
Complicated stuff. You know what I mean?
Simple.
And even if, like, here's the thing. If you want to check it out, you can go on Wikipedia. But even if I were to tell you the steps in which the electricity flowed in a Tesla coil to produce these discharges, because it's a cycle, right? And it is very complicated, and I understand basically none of it. No, I understand something.
I mean, okay.
That's an exaggeration.
You understand a lot of it. I think you're just reading the wrong thing, because Wikipedia is significantly hard to read, especially on some of these topics. I feel like we definitely understand it. It's just a lot of steps. It's a lot of ways to actually get to the final thing, or not a lot. It's actually like two major things, but it's just broken up into like different parts. Like the only real thing that we need to like convey to you, the listeners out there, is simply like the theory of it working, right? So again, back to electromagnetic radiation or electromagnetic induction. Sorry, it's basically a very wound up coil, copper coil, whatever, just something that conducts electricity, that's going through very, very, very high amounts of voltage. Again, as you very well said, AC has the advantage of not attenuating on high voltages. So you can run very, very high voltages through it and you don't lose that much signal. So running like 10, 15,000 volts through it will generate a magnetic field. And the idea is that they're both working synonymously. Remember, a magnetic field generates an electric field, or a changing magnetic field generates an electric field, and an electric current generates a magnetic field. So they're all kind of related to each other. Again, without going deep at all, the easiest way to say what a Tesla coil is just a holy crap ton of voltage. Because remember, current is the flow of electrons. Potential is why the electrons want to flow. Potential or voltage. Remember, electric potential and volts are the same thing. So, they are. So, when I say the potential is high, and we already have, you listeners, we have a lot of experience with potential energy. We have a good understanding what potential energy is. So when the potential is very, very high, they want to go somewhere. So if you just run a Tesla coil, nothing will probably happen. You'll hear you hear the sound, but you'll be just seeing random sparks. But then you take something close to it, all of a sudden you'll see a spark, because that voltage difference was great enough for the electron to jump. Now, quick
correction. The electron obviously doesn't just jump, right? There's a lot of things that happen for it to go from there to there. So first up, I had a quick question. Why is it purple? That's a good question, right? Well, that's just because of our gases in our atmosphere. Nitrogen and oxygen have emission lines in the whitish, purplish, violet region. So when the electrons kind of knock them off, and remember, light is simply electrons dropping down an orbital and releasing a photon. That's all that light is.
Hold on.
When
that's not like light emission from a certain.
Yes, that's obviously what I meant. Yes, you're right. That's obviously what I meant, though. So yeah, so that happens as soon as the electrons are traveling. They're bumping down, up, down, like as it's moving through the atmosphere or moving through the air, it's creating these sparks. But again, all that is because of the high enough voltage that electron is able to get to its destination. So again, just in the air, there's no like lack of potential, right? But you bring this light bulb close to it, and now there's a Tesla coil. There's a huge potential difference that that the electron would want.
And it also requires a certain. I think it's called a. Oh, this is so wrong, but I think it's called like a potential break in the air. Where something with the conditions of the air causes, like, I think of it as like a potential tunnel where the electrons, like, once there's this break in the air, the electrons can flow across the air because of something. I'm not sure though.
Yeah, well, it's something on those lines, right? It's something on those lines. Tesla coils are basically just giant electric field generators. You can think about them that way if you really want to dumb it down, because that is what it is, right? It just wireless communication or wireless electricity, which is pretty cool. But that's basically the essence, right? That's basically the essence
actually,
of the coil.
I mean,
and I just really wanted to
a lot of wires.
I mean, there's a lot more. Obviously, there's okay, yes, of course, there are a lot of wires in the coil itself, but I'm saying there's a lot that actually also goes on with the coil that we don't need to really discuss. And if you want to discuss, go ahead and search it up. We encourage you to do your own research. Again, a big part of like these podcasts is to listen to what we say and then apply it yourself. You know, like listen, oh, that kind of sounds cool. Let me do some research. That is the perfect listener.
And I think you can actually buy a Tesla coil on Amazon if you wanted to. So
yeah, I'm sure you can. I'm sure you can. Okay.
Yeah.
Well,
I guess that is everything.
Anything else, Parker? Yeah. Fantastic. I'm just gonna do a quick little check if I forgot anything massive on Faraday. I'm pretty sure I didn't.
If you enjoyed listening to this episode, I do recommend that you go and subscribe to us on YouTube, or you just follow us as well on Spotify and rate this podcast 5 stars.
Boom.
Leave a comment if you want to be comment of the week. And, it is what it is. Thank you for listening. This has been episode number 106 of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.